Hi, everybody. Welcome to this talk about memory noisy neighbors. I want to start with this. Has anybody seen this? Positive affirmations for site reliability engineers. It's very funny. It's hilarious on YouTube. I recommend everybody sees it. Yeah, and yeah, I'm going to botch it right now. So watch it. Don't count on me. But it starts like this. It's nighttime. There's a lone site reliability engineer sitting at his desk. And he's looking, there are exceptions from production. He sees the rising cost of the cloud deployment, and he just feels so haggard and frustrated. And so he goes into meditation, and a calm female voice tells him, "Your pipeline is green. Your tests are well written and stable. Your friends and family understand what you do. You were born to deploy Kubernetes clusters." And so this got me thinking, like, why do we do this? Why do we choose to operate these systems? And for me, this is the ultimate affirmation. Your deployment is highly available and cost efficient. Users delight in the product and its performance. So this is the holy grail. I don't know how visible it is. Apparently not as well. For me, this is the holy grail. We want to have a great user experience. And users really care about performance, and the performance of our systems affects business outcomes. So you might have seen this from Amazon. In 2006, they published a case study showing that for every 100 milliseconds of added latency, they lose 1% of revenue. So this is relatively an old result from 2006, but over the years, there have been dozens and dozens of these case studies from companies, well-known, less well-known, showing similar outcomes. And I especially like this one from Rakuten 24, which is a Japanese online grocery store, where they ran an A/B test. The application had the exact same functionality. It looked the same and it felt the same, except for added performance. The optimized version had 400 milliseconds faster load times. And the benefits of higher performance were staggering. They had more than 53% increase in revenue per visitor. It's just amazing, right? And companies have started to understand how important performance is. Now, together with performance, users also care about functionality. And so your deployments might not be as complex as these extreme cases that were published by the large companies of their service maps. But users want more functionality, and your systems probably have gotten more and more complex over the years because users want better search, better recommendations, AI interactions, and generally more features. And as you have more complex systems, it becomes really hard to reason about performance. And so when performance degradation happens, it's easy to blame the spaghetti monster of complexity. Or the network, right? Yeah, it's the network, and that's why everything is slow. But you don't have to blame these entities where we don't have visibility or control over. In fact, a lot of the performance degradation just comes from plain old resource congestion on the systems, on the servers that we're working on that we just are not aware of. We don't monitor them, so we don't know that it's happening. So what if I told you that a small cabal of engineers developed a resource allocation technique that enabled them to run 50% more transactions on the same hardware, run a lot more efficiently, and to have factors of lower tail latency, like 5 times, 14 times lower latency. And that it's a secret and nobody knows about it. That would be, you'd be angered, right? Like, how can they not tell us about it? They developed this thing that's so useful. It turns out they have told us about it. Over more than a decade, there have been more than a dozen papers from well-known universities and your hyperscalers showing us, like the community, how to deal with noisy neighbors. And this was early research up to, I think, today. There's enough out there that we can make useful systems for the entire Kubernetes community to benefit from. And I hope by the end of this talk, you'll understand what noisy neighbors are, what are the benefits of solving it, should we really care about it, the different mechanisms that exists out there and the types of systems to solve it, and what we're doing in the community, in the open source Kubernetes community to solve this. Just a little bit about me. I did my PhD in noisy neighbor mitigation. I then, specifically network noisy neighbor mitigation. I then started a network monitoring company that we sold to Splunk, and I'm now a maintainer of the OpenTelemetry network project. And I started on variants to solve noisy neighbor. All right, so let's start with the problem. What is noisy neighbor? I want to say, let's see what the effect it has on our workloads, and do we actually have it or not? Cloud native applications ultimately run on physical server hardware. And so the applications need to share the finite hardware resources that the servers offer. When one application uses more than its fair share of resources, then other applications cannot obtain those resources, and so their performance degrades. And in this talk, I'm going to focus on the memory subsystem, which is the shared last level cache, which I'm just going to call cache, and memory bandwidth. So let's see how a cache noisy neighbor affects an application. So this is how an application might fit into the different caches and DRAM. You have the blazing hot working set in L1 cache, and then the hot, warm, and cool working sets in L2, L3, and DRAM. When a noisy neighbor comes in, it uses the cache, it pulls a lot of memory into the L3 cache, which is shared among all of the cores of a CPU, and pushes your application out of L3 cache. So now all of these memory accesses that would have gone into this 20 nanosecond L3 cache now have to go to DRAM up to 250 nanoseconds, more than 10 times the latency to fetch each piece of memory. Their performance degrades. In the more extreme case, where the noisy neighbor arrives at the hyperthread next to your application, it might kick your application out of L2 cache. So now even your hot working set moves into DRAM, right? And now, so that these accesses that would have taken 4 nanoseconds now have to take up to 250 nanoseconds. So that's 50 times more. So you can understand why the performance impact can be massive. And in fact, it has been measured to be massive. So Google ran an experiment on their production workloads and published the results. This was a 2015 paper called Heracles, where they took the production services. Web search is the Google search node. ML cluster is a user-facing machine learning text classification system. And memkeyval is an in-memory key value store, like memcache. And so they tested with different load on the system, that's the x-axis. They measured the slowdown with the different noisy neighbors. And they found significant degradation from cache and DRAM noisy neighbor. You can see web search suffered up to 5 times degradation, ML cluster 5 times, and memkeyval 14 times. So there's a huge increase in P95, P99, what we call tail latency because of noisy neighbor. I want to run a little survey here. So please raise your hand if what type of nodes production user-facing cluster is using. Is it right, like the size of the nodes? All right, now leave your hand up if you never use a fraction of a physical CPU. You never use a fraction of a CPU. You never use the 4-core. You never use the 8-core, right? Still, nobody. Okay, nobody uses bare metal machines. So think about this. Best practice today is to separate our big data analytics from our production user-facing clusters, because you don't want to have somebody run a big analytics job and just destroy performance for the user-facing traffic. It turns out if you're running this way, and you're using like fractions of a machine, then what you're actually running looks like this, right? Where, you have other people running their workloads next to your interactive cluster because you have VMs running next to you. You're using fractions of a machine. Your cloud provider is giving away these other slices to other users. So you're actually running next to some random dudes on the internet, right? Running next to their workload. So it's looks like this. And does your cloud provider actually protect you from noisy neighbor from these other VMs running alongside you? I haven't been able to find evidence that they do. I believe they don't. And I think how absurd it is. We spend engineers on our teams or us, we spend months or years optimizing these deployments, right? We add database indices or change database indices. We change data schemas so that queries load faster. We might take services and break them down to multiple services so that queries run in parallel, or plain old profiling and solving bottlenecks. And we put in all this work, and all that work can be obliterated, destroyed by some noisy neighbor running alongside on the same compute infrastructure, just degrading the compute infrastructure underneath our workload. And so this is why one takeaway is, if you're running, let's say, order of 1,000 cores in production, you should prefer fewer, larger VMs to a lot of these smaller 4-core, 8-core machines, because then at least you know that the noisy neighbor next to you is going to be your own workload and not some random batch analytics workload, which is not as well behaved. Now, do you need to have batch analytics running alongside you in order to experience noisy neighbor? The answer is no. So in this research paper from MIT, they ran Memcache alongside a garbage collected workload. And you can see on the top graph, memory bandwidth on the machine is relatively low as the experiment runs. But once garbage collection starts, garbage collection is very memory intensive, the mark phase. When that starts, memory bandwidth saturates. And if you look at the bottom graph, which is latency, the latency of Memcache was very, very reliably 99.9th percentile, 50 microseconds, but then increased 3 orders of magnitude, 1,000 times during the mark phase due to the memory contention. So definitely you don't need to have big data analytics in order to experience noisy neighbor, and garbage collection can do it. And if you have a service that once in 10,000 transactions is huge, it has to touch a lot of rows in the database, maybe that is noisy neighbor to your own system as well. So let's recap. So far, memory noisy neighbor just increases tail latency by factors, like 5 to 14x measured in production. And anything can be noisy neighbor. You don't need batch analytics. Like, if your peer VMs could cause it, or your own workloads. What can we do if we solve the noisy neighbor problem? What benefits do we get? You might know one of these surveys. This one was published by Datadog, showing that more than 65% of containers use less than half of their requested CPU. They run at low utilization. And so I want to run another survey. We don't have many of these left, so just this one. So please raise your hand if you know what the average CPU is in a cluster that runs in production user-facing traffic. All right, we have some hands. Leave it up if it's more than 20%. Okay, a couple people lowered their hand. More than 30%. Keep your hand up if it's more than 30%. Nice. More than 40%. Okay, I think most of the hands went down. More than 50%. Oh, we have a couple with more than 50%. That's amazing. So if you said between 20 and 40%, you are in very good companies. So some of the largest companies on the planet with large engineering teams capable of optimizing their deployments have published their average CPU utilization to be between 20 and 40%. But what happened over the last few years is that some companies published results with quite substantially increased efficiency. So Google was 35% around in 2011 and increased to around 50% in 2019. And if you read published work, I've been able to find 2 major contributors. One is advancements in vertical autoscaling, which has been packing, like right-sizing the CPU and memory requests and then reducing waste that way. And the other one is handling noisy neighbor, and so reducing the tail latency and the ability to run more workloads on one machine. So I'll talk about it in the next slide. So here's a simulation just to visually show why you can get increased efficiency. Sorry, of why we run at low efficiency, actually. So on the left side is a simulated machine with high load, right? Like a lot of garbage collection events that saturate the memory, right? And when it's running at low load, there are less of these high memory events, right? And you can visually see why tail latency would be low. Like the P95 would be lower on the low load machine, right? Like it has less of these contention events. And so we've been programmed to when there's bad P95, we scale out so that we have lower load, right? So it looks like this. We have high load, so that causes memory contention. Memory contention because we saw the noisy neighbors kick out your application from caches, what we saw a few slides ago. The CPU efficiency drops. Now you have to wait for memory. And so our applications are slower and we have bad SLOs. Our P95 is bad. And so what we've been programmed to do intuitively is scale out, reduce the load. And in fact, I think this is an anti-pattern. We should not do this. This just leads to low utilization. What we really want to do is to solve the problem of this memory contention that causes the low performance. So what can we do if we can mitigate noisy neighbor and run at higher load? We can just scale down our systems, so run on fewer systems and reduce cost. We can also deploy more features that we couldn't before because then we would have breached our P95 SLOs and have a more featureful product. Or we can just roll it to our users and improve their SLOs. And if the hyperscalers have it, why shouldn't everybody have it? We need access to this as well. And it brings us closer to our holy grail, right? Like it touches on three of our important topics, like cost efficiency, the product, and the performance. All right, so what tools and mechanisms do we have to mitigate noisy neighbor? We'll talk about hardware and software mechanisms, Linux, what Linux gives us, and how do we create a full system that mitigates noisy neighbor from this? Modern CPUs actually have controls that allow you to specify for each application how much cache and how much memory bandwidth it should get. It's pretty great. Even if you don't have CPUs that support this, as these are the high-end CPUs, then it's still possible to control noisy neighbors by limiting the opportunity that they have in order to create noise. So reducing the number of cycles that they have. And you can do it by pinning the noisy neighbors to some small number of cores and then reducing the core frequency if you need to. So we have mechanisms to mitigate. Linux actually has support for these mechanisms, but not in C groups. I get this question a lot. C groups containers should protect us from performance degradation, right? No, they don't. The memory and CPU C groups deal with the number of bytes and the number of cycles each application gets mostly, and they don't handle memory bandwidth or caches. And this is partly because when Intel wanted to contribute this functionality into the Linux kernel in 2016, kernel developers wanted the capability of each thread to ask for its own allocation of cache and memory bandwidth, like CPU set. CPU set is a mechanism that each thread can say, I only want to be allocated on these cores. And C groups was not the right fit. And there's also some hardware limitations that made C groups not as good of a candidate. And the implementation ended up in a system called res control or resource control in the kernel. And it's a file-based API in sysfs. Also, we want to solve this problem and address memory contention. We have the mechanisms to do it either via direct control or through core pinning and frequency scaling. So how do we build a full system out of this? We care about the application P95, the SLOs, right? So let's measure the SLOs and then see if an application is really fast and some applications are really slow. Let's move resources from the fast to the slow, right? Like a Robin Hood allocator. So that could have been nice. There are some papers exploring this, but the problem is that measurements are very noisy because you're measuring P95. So you already have to average over hundreds and hundreds of requests in order to get a good reading of what's happening in the system. It reacts very slowly. Second approach, okay, let's look at CPU efficiency. The CPU wants to execute some number of instructions. If it has to wait for memory a lot because data is not in caches, then the number of cycles it takes to execute those instructions is high. If, on the other hand, if the memory is very close and it's really easy to read it, then number of cycles is low for the same instructions. So the ratio, cycles per instruction, is a good metric to know if your application is suffering or not. So we can use that maybe. The problem that this is also noisy because it depends on the exact transactions that are happening on your system on this mixture. Are they more memory intensive? Are they more compute intensive? And different transactions, like different code paths, can have different instructions and different characteristics. And the other problem is that it is complex. Just because different applications behave differently, cycles per instruction is 3 cycles per instruction. Is that good? Is that terrible? You need to profile the applications beforehand and keep that. And you need to do this for every version in order to see if a reading is good or bad. This is not a great system. But we talked about Google. This type of system is what Google deployed. And in 2013, they published a paper that this type of system was on all of Google's shared compute clusters. The third type of systems that you find papers about is reading the utilization directly, right? So you measure for each application how much memory bandwidth it's using, how much of the caches it's using, and if one of them is using more than its fair share, you limit it. So that's the most direct controller. And this is great. This is not noisy, and you can measure it, and it reacts very quickly to changes. So this is a good type of system. And in fact, in this paper by Alibaba Cloud in 2020, they said they had deployed it in production for over 2 years on an order of 1 million cores. So this is a valid system type. And in fact, I think this is what the Kubernetes community should strive for. So back to this simulation, right? Like the events that we're dealing with are on the orders of tens or hundreds of milliseconds, sometimes down to 1 millisecond. And so if you look at the reason why the noisy systems just don't work is because look at how, if you average over multiple seconds, look at how it looks, right? Like you just can't get any signal out of the system. And in fact, a lot of the measure, and this is what I show, right? Like by the time you make a decision, if you have noisy data, it's like the damage is already done and you haven't made the good decision. We found that you need to measure this at 1 millisecond intervals, and that's what we set out to do. And we started a new collector called the unvariance collector. In the interest of time, I'll show you just a little bit about the challenges that we had with the millisecond collector and then conclude. So what you want is to measure every millisecond on all the cores of the system, take a measurement, and then you have this measurement interval, and you can reason about who's using what in that measurement intervals. But what you actually get is like this. You have a little bit of jitter. And if you have a lot of jitter, it becomes hard to reason about what are we measuring? What are these metrics? Can I add them up? Can I analyze them this way? So the question is, do we have a lot of jitter or not? And so we ran this experiment, and this is what I wanted to show you in the second to last slide, where we measured, you have these 1 millisecond boundaries, and we measure how the first core that registers the timer and the last one, and what is the difference between them? Or like how long do they take out of these 1 millisecond boundary? On the top, you have a machine that has around 5 microseconds of like between the first and the last core to respond. So out of 1 millisecond, that's great. On the bottom is another one that has up to 300 microseconds, so that's 30% of our interval, where you have this jitter. And so we ran this on 2 machines of the same hardware, but one of them was the bare metal machine, and one of them was the extra large, the 4-core machine. And now the question is to you, who do you think is the metal and who do you think is the extra large? So who do you think is the noisy one? And it would be metal because there's 96 cores. It could be that because there are so many cores, one of them is going to be late, right? Or the extra large, only 4 cores, but the hypervisor does something, a noisy neighbor, etc. Who thinks the bottom one is the metal? Who thinks it's the extra large? Nobody's raising their one. Oh, okay. So there's noise there, and this is an artifact of the hypervisor. It's not really that bad all of the time. It's just when the cores are very idle, the hypervisor probably puts them in sleeping mode, so that's why they take a long time. But even when in the non-noisy measurements, the metal machine is a lot better than the extra large, so that supports what I said before. We're building this in the open. It's an Apache 2 license. And first, I'd like to thank our existing contributors. And I'd like to call on folks here if you're interested in contributing or joining the project. We'd love to have you. And you can make contributions to the repository, either to the collector, or right now we're building these synthetic workloads that we can measure and then check that the measurements actually are able to detect noisy neighbor reliably, right? Like we want to build these detectors on top of this raw data, 1 millisecond data, that find noisy neighbors. And so we want to validate it with these synthetic workloads. And the other ask I have of you is, if you have a cluster where you're willing to run this, we'd love to get more experience on production workloads to make this development work, to make sure that it does the right thing on a wide variety of workloads. So I'd love your help. My contact details are here, and you can make an appointment, Zoom meeting, and we can hop online. And so I hope with this that we can bring the community to kind of state-of-the-art efficiency. Everybody should be able to enjoy it, and I hope we'll get to our Zen moment with our deployments.